So in the last video, we talked about the constant volume heat capacity and some of the challenges to doing experiments at constant volume. So in this video, we're going to talk about the constant pressure heat capacity and why this heat capacity is a lot more helpful for us in the laboratory. So in the laboratory, CP is much easier. We can run things at constant pressure. Putting a beaker out on the lab bench means that our pressure is going to stay around 1 atmosphere. But this parameter becomes much more challenging to relate to the energy of the system. So really, instead of starting with internal energy like we did before, we're going to have to start with the enthalpy. So the enthalpy is given as H, and we can show, I kind of skipped this part in our first videos, but with the same sort of Laplace transformations that we were working with in this first section, we can get to this relationship that H is equal to E plus PV. And so from there, we can do what's called a total differential. And so I'm going to basically take the derivative of this. And so that means that I'm going to take the derivative of H, and it's going to be equal to the derivative of E, plus now I have to apply the product rule. And so I have PdV, so first times the derivative of second, plus the second times the derivative of the first. And then we can substitute in our first law of thermodynamics, where dE is equal to dQ plus dW. And so we get this relationship here. And now we can go one step further, and what we're going to do is we're going to plug the definition of dW into dH, and we get that dH is equal to dQ minus PdV plus PdV plus VdP. But now we also have to remember that we're doing this at constant pressure. So that means that dP is 0, and so this term goes away. And since we have a positive and we have a negative, these cancel each other out, giving us that dH is equal to dQ. Well, if the heat capacity is defined as the change of Q with respect to temperature, then that means that all I have to do is take the derivative of both sides with respect to temperature. And I get that Cp is the partial derivative of H with respect to T at constant pressure. Now, why is Cp more complicated? Well, it turns out that when we start adding heat to the system and the volume can change, that means that this energy that's going in, the heat that is going in, is contributing to two different things. Is contributing to both work and to temperature change. So if we thought about a two-level system, we have the energy of our reactants and we have the energy of our products. CV is a direct route because the only thing that the heat is going towards is changing the energy of the system. Meanwhile, if we have work being able to happen, the energy going into the system is both going to the work and to reaching the product. So if our work is helpful, in this case positive, then our CP is going to be smaller than our CV because our work is helping us reach our final answer. But it's also possible that work hinders us, thus making us have to add even more energy to reach the final product. Okay, so let's put this in perspective. CP and CV. So CV is constant volume. We add heat and the pressure is going to go up. And we find that CV is the relationship between the partial derivative of the energy and the temperature. Whereas if we allow the volume to change, CP is the partial of H with respect to T, and we can, with some work, eventually show, your book does this derivation, we're not going to do it, show that CP is equal to the partial of the energy with respect to temperature plus this PDV term. This is basically work. So what's going on here? Really, what we are doing is we are tracking the change of the energy with respect to temperature. It's just that at constant volume, we're able to measure energy, whereas constant pressure, we have to work in enthalpy. And this is okay for us because we know that these are just Laplace transforms of each other, and we know how to manage that.